Now, moving on, as I mentioned, um, the efficiencies that were given previously do not recognize cooling flows. Now, today's modern turbines run at such high temperatures that cooling is necessary and need to be bookkept, properly bookkept, in the design of these components. There, surprisingly, is no widely accepted efficiency definitions for turbines, and different manufacturers have different definitions. ADS has gone with a definition that is quite rigorous and will be defined in a moment, and has been well accepted by both military and major airframe companies that use gas turbine engines. And so this is the efficiency that has been built into the system. That is not to say that individual users can modify their input into the system to, in most cases, accommodate their own performance bookkeeping. And if they can't, please, they should contact ADS, and ADS would be very happy to work with you to accommodate your particular system. This next chart provides the efficiency definition that is built into the ADS system. And it can be seen that the numerator, first of all, is the actual work minus Q, and this is the heat that has been lost from the gas bath. Now, in textbook presentation, normally it's an adiabatic, assumed to be an adiabatic turbine, and that, for most cases, is a very good approximation. But the system does allow you to accommodate any heat loss if it turns out your turbine during transient conditions, or it may be a transient test, is not truly adiabatic. In the denominator, the first term is the ideal work of the mainstream gas, and this is the pretty traditional ideal work definition in the textbook definition. It's the next term, the summation term, which is unique to the cooled efficiency definition, and it sums the potential work that each flow can do. And so it would be calculated the exact same way as for the mainstream, from an upstream point to the downstream of the turbine. And typically it's at a supply temperature and pressure to the exit of the turbine total pressure. And so with that information, you can calculate the ideal work for each of the cooling flows, and they're summed up and added in the denominator. And that, in total, forms the definition for cooled efficiency. And again, if it's adiabatic and there are no cooling flows, the Q goes to 0, the summation terms go to 0, and you have your classical textbook definition for efficiency. Now this chart provides cooled efficiency information which has been added to both the row and overall output tables that were previously discussed. And so there are three terms that have been added. Looking down below, the white columns, is what you've seen before, the two previous efficiency definitions. And now the three columns that have been added is the mass flow, the total mass flow of cooling and leakage flows that have been added to the gas path. And the next column is the total temperature from the equivalent total temperature change for non-adiabatic conditions. So here we can see that this case was slightly non-adiabatic, and the last column provides the cooled efficiency correcting for the non-adiabatic conditions. And so you can see the cooled efficiency is slightly higher than and it's on a total to total basis, than the total efficiency, which is in the first column.